Okay. Once again, greetings, everyone. Thanks for joining the Active Inference textbook reading group. We are reading this year's 2026 publication, Fundamentals of Active Inference by Sanjeev Namjoshi, published with MIT Press. This week, we are starting Chapter 9. While Chapter 9 is still within the broader Part 2 of the textbook, as we get more specifically into modeling in terms of active inference and not simply based on sort of Bayes' theorem alone or making different kinds of linear assumptions alone, but rather bringing everything together now and looking at these core algorithms. Nonetheless, Chapter 9 is actually going to put us in a very different kind of space, a different state space, as we'll be focusing more on discrete state space models. We'll spend 2 weeks on this chapter today and then once again next week. And then chapter 10 will extend the state space models, discrete state space models even further. But for now, we're just getting familiar with the sorts of nomenclature as well as conceptions of how we view hidden states and observations, all the rest within a discrete setting. So first, before I go any further, I just wanted to briefly share this for anyone who's interested. Um, this is oh, that pasted well. Um, this is the computational psychiatry course being hosted this year online with University of Zurich and ETH Zurich. It's a really fascinating course. I won't spend much time on it because, of course, not everyone here is necessarily interested in psychiatry in particular. However, for the past several years, Ryan Smith, who has contributed a lot of literature and kind of progressive empirical work in the realm of active inference, and including in especially discrete state space models that we'll now be covering. He's given a tutorial on active inference, including how to set up POMDP models, which we will be hearing a lot more about as we proceed further. Um, but sorry. Yeah, so he will be doing a tutorial once again. There are links somewhere through here to find some of his open source code for those who are wanting to get into programming themselves. And furthermore, everything for this, except for his tutorial, I think, unfortunately, but all of the sessions that are being hosted can be accessed online, and it is very affordable to get a ticket to watch everything online. So it's running from September 7th to September 12th of this year, and can be watched entirely through Zoom at a much cheaper rate. To be clear, we are not sponsored in any way by TNU or University of Zurich. I simply want to make that available to everyone and let them know that these resources are available. And they also do have lectures from previous years, gives you a sense on different ways of sort of integrating these things that we're learning about computational modeling, at least with sort of models of the mind, including in the context of psychiatric disorders, symptomatology, understand different ways that cognitive science and other fields that are not necessarily focused on psychiatry, nonetheless, have dialogue with psychiatry and vice versa in the development of these models. And then interestingly, of course, we know that the textbook we're going over is for engineers, not necessarily those who are specifically focused on the brain, nor any sort of psychiatric disturbances the brain is experiencing, right? So it's just to say that there's a lot of sort of dialogue going on between these fields, and they all sort of learn from one another whenever we have those who develop more complex but interesting or accurate algorithms versus the kinds of empirical work that's done with respect to behavioral studies and neuroimaging, data analysis, and so on. So wanted to make that clear. And then furthermore, for those who are interested in coding, I want to share. We've brought both of these up before, but this first one is SPM. This is a library that's existed for decades at this point. I think it was either the late 90s or early 2000s that it was started, and it's grown significantly. And everything that we're about to witness in chapters 9 and 10 does have dedicated scripts in SPM for carrying out these kinds of functionalities. So I think we'll want to see. The only thing is that many of these files have, very technical names as they've sort of grown over time. But like this file here, SPM MDP VB underscore X, this is effectively code that we can use to make what are called hidden Markov models or Markov decision processes, including partially observable Markov decision processes. That's that POMDP model I mentioned earlier. Um, this provides a significant amount of just kind of syntax and something to sort of look at and get familiar with. Of course, SPM is a library for MATLAB. I'm able to share this code with you because it is open source, but MATLAB itself is proprietary. There's no requirement that you learn MATLAB specifically in order to do active inference writ large. But nonetheless, as I said, SPM has been highly kind of specialized and developed and improved over the years. There are many published simulations in active inference, including in discrete state-space models that specifically will reference how they used SPM to carry out their simulation and design it and all the rest. And hopefully they've released that code, which will then work so long as you have MATLAB and SPM so that you can try it yourself. But here we'll see all of the different sorts of variables that we will be encountering in chapters 9 and 10. And we will see kind of how these different matrices are constructed, categorical probability distributions, and all the rest. I will pause there because, of course, we're not quite there yet to be able to start catching on to what is going on here. So what I would really prefer to do is first bring us back a little bit. In fact, back to chapters 1 and 2, roughly, because as I've mentioned, we're switching into these discrete state-space models. And so it's not as simple as taking one-to-one everything we've learned thus far and then relying upon it in order to develop these discrete state-space models. However, what I do appreciate that I think I interpret from how Namjoshi's written the textbook is that now that he's established everything for the continuous models, we're able to see these kinds of analogs between how continuous models and discrete state-space models are created and how they run inference and learning and all the rest. That is, they're obviously not equivalent, but conceptually, if we sort of lined everything up between each of them, we would be able to draw connections between how one component works in the continuous case versus how it works in the discrete state space. So I think that learning by analogy is probably the fastest way to make this sort of quick transition from chapter 8 into chapter 9. So with chapter 1, we recall we were presented with the inverse problem, which is, can we infer hidden states using observations? And the other way around, can we, if we know a hidden state, can we then predict what the observation sort of should be? We covered this very broadly and in depth over the first 8 chapters, but now we're simply going to change how we're thinking about our X and our Y, our hidden states and our observations. That is, how is everything encoded? We saw that in chapters 1 and 2. We were presented with these normal distributions or Gaussian distributions, and they have their own respective parameters with a mean and a variance term. And so this is where we're thinking in terms of scalar values. We're thinking about values like 1 and 7.9 and 3042.62. Those are the kinds of sensory observations we're receiving. Those are the kind of values that we find whenever we're inferring hidden states, right? And then whenever we have a multivariate case, we have multiple hidden states, all being linked to potentially multiple observations that are being received simultaneously, such as observations through the eyes and through sense of touch and the rest, all getting linked up to these different continuous hidden states. But still, we're thinking of these continuous numbers or values, whereas For the discrete state space we're switching to, instead of using these normal distributions, we're now going to be using predominantly categorical distributions and another kind of distribution known as the Dirichlet distribution, which we won't cover today, although it'll be very clear whenever we get to it how it relates, and it's incredibly similar. Um, a categorical probability distribution, instead of viewing things as a continuous scale of, if we could say in the continuous case, the expected mean of a hidden state went from 2 to 4. And so we actually have this continuous scale we can look at. We can say it increased, the mean increased by 2, 4 minus 2 is 2, as opposed to the categorical case where we can't quite do that. We don't have a continuous scale. We're instead thinking, and this is where it's worthwhile to become at least a little bit familiar with basic probability theory, including things like, what is the probability of heads whenever we flip a coin? Uh, Assuming it's a fair coin, we know that probability of heads would be 0.5 and probability of tails would be 0.5. They're equally likely, they're equally probable, let's say. Uh, and those are two mutually exclusive states that the coin could be in, or from our standpoint, it's two mutually exclusive observations that we could receive when we look at this coin. So we could represent that as a categorical probability distribution. Instead of it being a normal distribution that's parameterized in this way with a mean and a variance, instead, categorical probability distributions can be much simpler in the sense that it's just a vector where each index refers to a particular mutually exclusive state, and the value represents probability. So we could have technically, heads or tails would be 0.5 for heads, 0.5 for tails. And anytime we do some kind of computation, we'll just remember that the first index is referring to heads and the second is tails as our two mutually exclusive states. And so these slides, which I've been sort of slowly adding to over time whenever I'm able, I just linked them in the chat. Um, this is a much earlier slide, just trying to portray like these are the different ways that we approach active inference from the and not just active inference, but more broadly, all of the problems that we approach whenever it comes to machine learning and deep learning, and in certain ways, even what LLMs do. We're working with these different kinds of not just distributions, but generally thinking about how do we encode information? How do we encode the world, so to speak, that then allows us to sort of run computations over those various encodings? And whenever it comes to trying to do empirical modeling, where we are the experimenter trying to build a model that represents a world or a particular phenomena, we do have to imagine like how would our model conceive of and encode these different kinds of information. Um, so with categorical probability distributions, again, we're not looking at these continuous values. There's also no assumed ordering, right? Like 0.5, 0.3, 0.2 for these hidden states, sunny, cloudy, and rainy, we would say those are like hidden states. Like these are the states of the environment. We have to infer, perhaps the observations are, is it wet? Are there is the amount of light that I'm seeing in my visual field very high or very low? Um, are there different kinds of shadows that I'm seeing because of clouds in the sky? However you like, it's just supposed to be an intuitive example, but it's just say if we treat those as three mutually exclusive states, we're not saying that cloudy is quote unquote more than sunny and then rainy is more than cloudy, right? They're all sort of on their own flat sort of playing field here, and we're not comparing them in terms of one of them having some kind of higher value than another, whereas that's exactly what we were doing in continuous active inference, where we're looking at where do values lie when sampled, and how does that distribution look, and we're able to make those kinds of statements of something being inherently bigger or smaller than something else, right? And then finally, whenever we compose a distribution like this, all probabilities need to sum to 1. right? So we're always thinking about this as sort of like proportions. If you were to add up all the bars of sunny, cloudy, and rainy in this probability distribution regarding these three mutually exclusive weather states, if we were to add up all these bars, they would just sum up to one. So we're thinking in terms of sort of proportions, or we can say that maybe something is more probable than, like, one state is more probable than another hidden state, but that has to refer back to these values, right, in the distribution. Um, so um, after that slide, we proceeded on to chapter 2. It said now we'll move to chapter 9. And there's quite a bit more going on here because I attempt to make these slides as sort of um, not quite as dense as possible, but I'm attempting to sort of get at a lot of information at once, such that one doesn't have to repetitively go back and forth between different slides and the rest. Um, so what I've done here is section 9.1, tried to lay out this continuous versus discrete state space perspective on the modeling that we're doing. In the top, these are all things that should be familiar. Some of them go once again back to chapters 1 and 2. We know that we are always here starting with Bayes' theorem. We're not even talking about variational Bayes yet. We're not talking about free energy yet. We just know that we're always employing Bayes' theorem in this kind of Bayesian framework. In the continuous case, you recall, um, we have our posterior being equal to our likelihood times a prior all over model evidence. That's the kind of nomenclature that we can use. It's effectively X representing hidden states and Y representing observations. And then whenever we kind of write that a bit differently, we can actually take the joint distribution between X and Y, and we can say that is our model. Our model is something that kind of encompasses this broad distribution over hidden states and observations, such that if you wanted to ask of the model what is the probability of receiving a particular observation given some hidden states or some other such thing, we could effectively have that whole joint distribution needed, along with, as long as it has some priors and a likelihood as its parameters, we could compute its probability. So we're able to sort of query this model and this broad distributional space that it encompasses in order to find probabilities. That's kind of what we do with our models, right? We predict probabilities using hidden states and observations. And then whenever we look inside of what the continuous model looks like, as I mentioned earlier, we see that we were using these normal distributions to set up our likelihood and our priors. Now, something very simple, whenever we switch to the discrete state space, is that we are still using Bayes' theorem. In fact, if you compare equation 1.2 and 9.7 being for continuous and discrete respectively, they are the same thing. Um, some may or may not like that we're switching out X for S and Y for O. But in my own personal experience, as well as seeing that it's already been pretty well established in the literature, it is very useful to just remind us of what kind of state space we're working within. And it's also a good reminder in that X, of course, in the continuous state space is going to look like some kind of distribution, here a normal distribution, whereas our S in the discrete space, our S hidden states, are going to look like these categorical probability distributions that I was referencing. And so if we compare how the model is defined and what it contains, in the simplest cases, we know in the continuous setting, our model contains a likelihood, a state prior. It contains a generating function, which is essentially just sort of how we get to the likelihood. That's how we get to the model's ability to relate hidden states with observations. And so from there, we just have some parameters. Now, this will look much simpler in the discrete state space setting because technically our observation model, which is like our likelihood, and our state prior, which is conveniently titled the same thing with continuous, both of those also represent priors over hidden states, and they represent the relationship between observations and hidden states, right? So here we have, and we name each of these a particular letter. We use A as a shorthand to refer to the probability of observations conditioned on states. We use D to simply represent the probability of hidden states or prior hidden states. So you can see how they're very analogous, right? Probability of Y conditioned on X, probability of O conditioned on S. Those are the analogs between continuous and discrete. And similarly, the probability of X versus the probability of S, right? Those are our priors. So I've attempted to sort of link these things together. We can see how we can go from a prior distribution in the top case down to what looks like a discrete prior distribution on hidden states in the discrete case. Same thing for likelihood. Another thing that we can do is that for any particular observation in the continuous case, we would use this Y hat symbol where we're effectively clamping an observation. That way we can query our continuous model. Well, if I receive a particular observation, an observation with a particular value, can I say what its probability is? And there's a little bit more to it than just this, because you recall that, the probability of any single particular value is technically zero when we're looking at a continuous distribution like this. But whenever we're able to kind of slice things up and discretize, that's where we are able to make statements about probabilities. Whereas here, in the discrete state space, it's actually a little simpler and more complex at the same time. It's simpler in that really we're still just looking at these mutually exclusive states and observations. So here we have four hidden states, both of these boxes for the prior and the likelihood for this example discrete model. They're coherent with one another. So that this is the prior for that discrete model, and this is the likelihood for that discrete model. Again, call that all probabilities sum to one for states. And then for the likelihood, similarly, all of these columns will sum to one. So we're still very much in that kind of domain of making sure that it's a proper probability distribution. We can't have one value being 0.5 and another one being 1.3, right? It would kind of overflow our limit there. We would need to normalize the probability distribution to put it onto a scale of 0 to 1. So that is something we could do, and we'll get back to that with Dirichlet distributions in future. So we're looking at a case where we have four hidden states: rainy, cloudy, sunny, and snowy, and then three different observations that the agent could receive, which is water, hot, or bright. It's not the most intuitive example, but I think it's good enough to get at the point of here are sort of the three different sensory observations the agent could receive. And we're going to consider all those to be mutually exclusive. That is, an agent could only perceive water or hot or bright at any given time step. We're still in this world of time steps being run over the course of a simulation, or a simulation that is comprised of capital T time steps, where a step of inference happens at each time step. So at a given time step, an agent might witness water and then infer that it is rainy because there's a high probability of that hidden state. We've not actually talked about inference in the proper sense just yet. We've just talked about priors and likelihoods. And those will actually act as kind of formally how we use these words parameters. Those are sort of the parameters for our model. I'm not gonna speak too strongly on that point because it can be conceived in different ways, and I want to make sure that I understand how Sanjeev wants to present that kind of material. We're just going over sort of the fundamentals of discrete state space models today. Um, but in any case, you can just see from comparing, like, this was the simplest model we essentially saw in chapter 2, this continuous one. And whenever we move to discrete state space settings, the model is even smaller, right? Like these are kind of effectively the parameters that contain all the information we need. They contain these full probability distributions such that we could probably arrive at Bayes' theorem from there, given that we receive some kind of sensory evidence, right? As long as we receive some new observation, we could run that kind of computation. Um, what gets introduced after that in roughly sections 9.2, 9.3 is where we also add state transitions. And while I haven't represented this exactly how I would like to on this particular slide, I at least have enough information to get at the points that I wanted to sort of illustrate here, which is that not only do we have a prior and a likelihood, but you recall that in roughly chapter 6 and going forward from there for continuous models, we have this situation where we introduced flows to hidden states. We say that hidden states transition over time. That's in the case where we have a model that's capable of making inferences about a dynamic environment. So not only do you have your A likelihood where you relate hidden states to observations, as well as your D, your priors on hidden states. But now with this new B transition matrix, we're also able to have an agent who can make inferences about how the hidden state changes over time. It allows for, so it effectively adds this sort of temporal dimension to an agent, right? In a static environment, if we're just thinking purely in terms of computation, not too much respect to let's say, we're not using an example of a person who's making decisions and thinking about empirical work. We're just thinking more generally to understand these fundamentals. If you have a prior and a likelihood, then that means any given observation you receive, you could compute some kind of probability. But nowhere in any of that do we have some sense of how time works or how the hidden state might change over time. That entire dimension is lacking, right? It's just, you push a button and you make an inference and you're done. Here, we now that we have the B, we're able to sort of compose everything together and say that the probability, first, our generative model is for all time steps, where the agent actually has a sense of how one time step can shift to another, and the hidden state can then shift from the current to the next time step. And I want to be clear, and sorry for mixing up my words here, but we're still working with these kinds of Markovian assumptions. That's why we have these phrases, hidden Markov model, which effectively is what we're looking at here. A hidden Markov model has these Markovian assumptions baked in. So there's this kind of timelessness sense where we're not necessarily baking a bunch of historical information into our model. It's simply saying that it's able to make an inference about how the world changes from one time step to the next, not necessarily from one to the next to the next to the next, just one to the next. We'll kind of supersede that going forward by the end of this chapter, I think. But for now, we're just looking at these kind of foundational pieces to the hidden Markov model and discrete state-space models. So we're effectively just saying that this agent has some initial priors about hidden states, the states of the weather, their respective probability. What's the prior probability of it being rainy or cloudy or sunny or snowy? We can imagine if one were in Antarctica and these were the only four things we could choose from, maybe their prior on snowy would be incredibly high. It might be the only thing. It's this, of course, the reason why this isn't intuitive is that we can imagine it being sunny and snowy at the same time. In this kind of model, we're saying that can't happen. These are mutually exclusive states, right? So, there are many other examples that we can use aside from this to try and get at the idea. Heads or tails with the flip of a coin is much more intuitive, right? Because we know it necessarily can only be heads or tails in reality. Um, so we have our priors, we have our observation model or our likelihood. Again, that's that A, and it's how we relate observations to states. And then here we have the state transition model. So again, with the continuous setting, we would have an agent who had some kind of transition model within itself. It's effectively giving it a belief that hidden states can change over time, irrespective or without any reference to what's going on with the observations. It's rather that all this information kind of gets integrated together over the course of inference, right? It's like given this one observation, Like, what do my priors say about hidden states? What does my observation model say about hidden states with respect to this observation I got? And then what is the hidden state based on how I think the hidden states change over time? Now integrate all that information. And that's sort of the general notion of inference that we've been following, barring for talking about action, which here in chapter 9, or at least early in chapter 9, we're not talking about action at all. Similarly to continuous state-space models earlier in the book, we didn't jump to action. We only got to action whenever we reached chapter 7, I believe, right? It took some time to get there. So now here, we're not immediately getting into action. We're just talking about perception, which is where we receive an observation and infer hidden states. So these are all the sort of components that go into that for discrete state-space models. And then we can view how that looks a little bit more clearly in these equations. First, we're going to we saw that there are all kinds of nice properties of logarithms. And whenever we do these kinds of log transforms back in the continuous setting, right? By taking our precisions and using a log transform, we're able to do different kinds of operations with them whilst helping them stay on a non-negative scale, so that everything can work properly. But then we're able to sort of convert back between log and non-log in order to do anything that we need to do. So we're going to do a lot of that with discrete state space models as well, whenever we take the logs of these matrices at times. And I also included this equation in part because I think something that gets overlooked whenever people construct these models is that um, while it is very important to supply your D vector or your D matrix or tensor, it's going to depend on if you're in a multivariate case or a univariate case. We're just looking at the univariate case. All of these have been for the univariate case so far. We're just looking at one set of observations you could receive, like one observation modality, and then one hidden state factor. There's only one hidden state of the world. It could be one of these four. There are three different observations in this world. At any step, I'll only get one of them, right? So in this univariate case, our D will be a vector, just as we've seen. Um, D is only kind of used in inference during this very initial time step, right? It is our prior, and in all senses of the word, that's our starting point. If I go to Antarctica and I haven't observed anything yet, my prior is probably going to be that it's going to be very snowy there, right? I've not seen any observations yet, but as soon as I receive an observation, if I were sort of following the way the mathematics are composed here, as soon as I get that first observation and I incorporate my prior belief that Antarctica is going to be very snowy, is once I get that observation and we move on to the next time step, we're no longer in this world where we're thinking about what those prior values were, because I've already updated my posterior, right? I've already updated that, and that's going to effectively become my beliefs going forward. So the D is, yes, an essential part of our model. But I think what can happen whenever people start modeling is that they take D to be this extremely important thing that's going to have a major impact at every single inference step. It's not necessarily the case. We will get there in terms of talking about learning, in that whenever we went over continuous models, we moved from talking about perception and inference to learning and then finally attention, where learning is updating our model parameters. We have that same kind of process with discrete state-space models, where the parameters can get learned or updated. In that case, we will actually update the D, we'll update the A, and all the rest. If you're running some kind of simulation with an agent, that would be expected to occur over time, to where there would be learning of parameters, and you might run some kind of behavioral experiment where a participant or a mouse or whatever your test subject is, say they undertook multiple trials where we run multiple simulations using the same sort of agent there, then in that case, you would employ D at the first time step of each of those. So if you did have learning on the D, then that would matter. It would start to matter because you'd be changing the D over time. for all intents and purposes, if you're just running some simulation because you're trying things out, you're still learning how all this works. Or if you're actually employing a model for the very first time and you're trying to fit it to some empirical data, but you have no idea what the priors should be, in those cases, typically the D will be initialized as being fully uniform. What does that mean? A fully uniform distribution would look very close to how this cloudy illustration here looks in our A matrix, right? Every single state has the same exact probability. That relates to this notion of the maximum entropy principle from a mathematician and physicist, E.T. Jaynes. Uh, and the general sense is that by beginning with a very uniform prior, you're allowing the model enough flexibility to start learning in a good direction. That is, you're not giving the model any preconceived notion that any particular hidden state is more probable than the rest, right? It's kind of like going into a situation. If you go into a situation where you're going to learn a new game for the first time, if you come in assuming that it's going to work like all the other games you played before, you're going to find yourself getting really frustrated whenever you get confronted with all the novel aspects of this new game and the fact that you do, in fact, need to learn it, right? So if you come in too biased towards thinking, oh, soccer is just like baseball or something, then as soon as you're presented with the fact that you need to hold a bat or something like that, you're going to be hit with a lot of surprise, of course. And then it's going to you potentially conceptually would have to do some kind of unlearning that you have to unlearn that you kick the ball with your feet. Instead we're going to be hitting a ball with a bat, or we're going to be throwing it. It's going to depend on what position you're playing and all these other sorts of distinct rules, right? So you would need to the general idea would be come in without any strong preconceived notions, right? So that's one way of thinking about the D. That is, it only occurs at the very initial time step in any simulation, and then it can be learned, but learning it only becomes relevant if you're running multiple simulations where you will once again start at a new time step zero in the next trial or the next simulation. And then also, if you're unsure of what to do from a computational or modeling or programming standpoint, it's very fine to initialize it as being uniform. Of course, in a psychiatry setting, or if in some other kind, whenever you're developing a model, a reinforcement learning agent model that you want to be safe, and therefore, you want it to sort of avoid certain states, or you want it to, have a certain understanding of states of the world to where, it's trying to realize certain ones and avoid other ones, then it might be the case that you would give it some kind of bias, right? You would bias its priors in different kinds of ways. So I also wanted to include back in chapter 2, and then over the course of chapters 2 through 8, we saw various kinds of graphical representations of these models. Graphical in the sense that they are quite literally a graph where we have nodes and edges. Nodes are the sort of circles representing our variables, and then the edges are just referring to there's some kind of relationship between the two things that the edge connects, right? So for figure 2.8, was a continuous model where our agent infers x as a variable, and it's going to use the variance and mean of x as its parameters because it was a normal distribution. And then our other node y, which was our observations. There's some kind of parameter. We didn't quite get there in chapter 2, is in chapter 3 that we saw more about these in learning. But nonetheless, it's effectively just these different parameters connect back to it. For y, there's some kind of variance or belief about the variance, but y itself is known because the agent directly receives it. That's why we don't see a mean value there. It's just it actually directly observes the y. But then there's some kind of hidden parameters, so to speak, that's conditioning y and potentially conditioning the relationship between x and y. It's quite a mouthful just to say that we can represent these models in terms of graphs. So figure 9.3 also makes the point that we can do a very similar thing for discrete state space models. And there have been different kinds of ways that these have been graphically composed. Though this figure on the left is closest to the kinds of Bayesian networks that we've been looking at earlier in the textbook. And Joshi does make the point that he will continue to largely focus on these kinds of Bayesian network graphical illustrations just to keep things more consistent. And sometimes it's a matter of preference, or sometimes it's a matter of trying to find different ways of illustrating different aspects of models that makes one graphical architecture sort of or notation. It makes certain things easier to represent or not with a model. Nonetheless, of course, we don't want to be we don't want to stray off course with any kind of arbitrary graphical designs. And so largely focusing on Bayesian networks, different kinds of factor graph models is what we'll frequently see them phrased as, or Forney factor graph models, just another kind of factor graph that conceives of nodes and edges a little bit differently, but we're still able to represent a lot of the same information. I also pulled in, this is from the previous textbook, and since it's freely available here, um, through MIT Press's website. One can just simply download the book. For anyone who wants some additional assistance with, getting into discrete state space models, they can especially look at chapter 7, active inference in discrete time. This was the textbook co-written by Giovanni Pizzulo and Thomas Parr and Carl Friston. And it's here that they also split up active inference into sort of continuous models and discrete models. And so we get these different kinds of illustrations, we get representations here of all the different ways that we can kind of compose these different parameters, the A and the B, the D. It also opens up with those and talks about hidden Markov models. So you'll see a lot of similarities. So I think that if there's any kind of confusion that arises, especially here in chapter 9, where we're just getting at the fundamentals of discrete models, it is a matter of opinion. I think that Joshi has done a really good job actually of getting at these without saying that anyone has to harken back to the previous textbook. Just simply making this known that it's available, and they give their own examples from previously published work. In a little bit more context on some of the different dynamics and components of these models that still are simply using the A and the B and the D, the same material, but we get them from different perspectives. Like here's an example where you have a person who knows what the script is for a particular song, right? So they have their own beliefs about what the correct notes are for a song, but then they're also listening. And so receiving these like audible observations of the real notes that are being played. And so the person, the musician, can kind of make inferences about what note they heard versus what note it should have been. And then we can see what happens whenever the wrong note is played versus their belief about what it should have been, and using different forms of plots and graphs and shading to show kind of how these categorical probability distributions look as things play out over time. I also very much like the 2022 textbook for those who are interested more precisely in neuroscience and neurobiology and the theoretical and computational aspects. We actually get these different kinds of like waveform patterns that start to align much more with a lot of the initial inspiration for this kind of modeling. And its purpose was to be in relation to neuronal activity, such as local field potentials, raw amplitudes, as well as like frequency um, analysis and kind of spectral analysis of different frequencies. In any case, Sanjeev nonetheless does a really good job, I think, of presenting us with something pretty coherent and relating continuous to discrete models. So um, before I go on too much further, I mean, I know I've spent almost the entire session so far talking about these, but I think it's really important in that if we miss the fundamentals of discrete models, it's going to be much more difficult to sort of catch up whenever we start expanding these models. Sanjeev has his own illustrations, but you can see in that chapter 7 from the earlier textbook I mentioned, like already we go from this hidden Markov model that we were talking about, where we have an agent who effectively receives observations, relates them to hidden states through their A parameter, their A matrix or A tensor, as well as using their initial priors, the D, which again you can see here, it's the D only starts the simulation. It doesn't technically persist, right? That's the timelessness of Markovian processes. We've sort of already updated our beliefs or posteriors from there, and then those can be used as themselves a kind of prior to be updated after that. So the D is kind of left behind. In any case, so all of that information is already something that needs to be understood fairly well, and understanding kind of how these graphical models work, and how these matrices are composed, and how, the basics of probability. These are mutually exclusive states, mutually exclusive observations. They're probability distributions that must sum to one between all of them. We soon get into the POMDP model, which I brought up much earlier. These are very similar in that they still have an A and a B and a D, but now we've added a few things, right? We've added a prior over observations themselves. And we'll actually, once again, we have all these analogs between continuous and discrete models. We'll see that the priors over observations in our C parameter are a bit similar to very specifically the bump, Gaussian bump example that we saw back in chapter 7. Here, the agent um, had capacity for action. And so it had these beliefs about exogenous forces, V. And what we did was that we fixed them. We kind of clamped them, right? And so Namjoshi referred to this as a kind of preference prior. It's almost as if by clamping or kind of making the belief about V static or stable, it's saying that this now no longer functions as something that the agent updates. Rather, it's a sort of fixed homeostatic set point, that it's as if the agent wants V to be that value. So here the idea was V was set to be 0 in the agent, meaning the agent wanted to be, at this vertical height. So whenever we get, if we imagine the agent in a 1D world of water where a wave coming through can push the agent upward, whereas the agent wants to remain flat on the ground at the first coordinate without getting lifted up. That is, the agent doesn't want to be pulled away or pulled upward by this wave. The agent says, "Oh, I want to be at this coordinate, so I'm going to exercise action that realizes that." That's this notion of self-evidencing. In simplest terms, it's saying that there's something in the agent that it sort of wants, or something in the agent that perhaps it even needs biologically or something, right? Like our bodies kind of expect roughly a similar number of calories per day, or roughly a similar number of hours slept per evening, and the rest. And so, by kind of having this belief in advance about these exogenous forces and all the rest, whenever they're fixed, means that we can act in order to kind of bring them into reality, right? This is what we want to happen. And so action here is sort of in the service of realizing our expectations. So if I believe that I'm hungry, or if I believe that I need food, or I'm observing that I need food and I want to see that I'm no longer hungry, I will eat, I will act, I will eat food, have caloric intake in order to realize that preference that I have, that sort of homeostatic point, set point of not being hungry, is the way we can sort of phrase that. And so we get very similar logic whenever we set these priors over observations, in the particular way that we're learning about these models. There'll be more in future about, you could have preferred states as well. You could do these things in very different kinds of ways. But the most canonical, I think, is kind of what's set out here in the textbook in 2022, and the way that Sanjeev picks that up in his textbook in 2026. And um, and I would say from there, anything else that I'd want to introduce you all to is that we've also heard many references to PyMDP, which, let me pull up their better website. Very cool. They gave a very nice presentation with the Institute late last year. They're also developers at the last IY International Active Inference Workshop, or International Workshop on Active Inference last year, which was held in Montreal. They've done many updates to this library. It's now kind of successfully reached a 1.0 version. So that there are many, in the sense that it's more or less intended to be fully functional with respect to the degree of functionality that they included. So I do think it's very worthwhile for those who want to learn to code in active inference, and especially discrete states-based models, worthwhile to get into PyMDP, as well as the different examples and tutorials that they provide. I think much of it was pretty well built out. We'll see references to this T-maze example. You can see worded references to the T-maze example back in the 2022 textbook. I think that Sanjeev may cover it. Given I'll be leading these groups, the textbook group, for the next few weeks, I will absolutely be giving at least one code demonstration in the next few weeks. It's more about which one to choose. There are many different ways that we could go with that. And again, it's very important to understand the fundamentals to creating these models before jumping too far ahead, right? Because I know that it can be quite interesting to create really complex models, but you know, to sort of use this old adage, simple as possible and no simpler, right? That's kind of that's part of the general idea of what the free energy principle is about in some senses. Almost philosophically, and so I'll say that here too. Sometimes the model that can be best, especially whenever it comes to getting started in learning, is to choose something that's simple as possible and no simpler. That is, it can demonstrate and entails all the things that you're trying to learn, but don't expand it beyond that, right? We don't have to jump to things like hierarchical models right away, or different kinds of complex relationships between hierarchies and all the rest. We will in fact come to that. And I think being able to really just understand the fundamentals, define them appropriately, and then being able to sort of define what your simulation should be, where you have a simulation that actually, at each time step over time in a real-time setting, it itself elicits these, clamped observations, right? It needs to be able to give an observation to the agent, one of these mutually exclusive observations, and the agent needs to be able to run inference. It needs to be able to do perception, that is, infer hidden states from that observation and perceive from the environment. And then finally, if we're in a case where we have action involved, where the agent can actually act in that environment, then the agent needs to be able to emit an action, which then gets sent back into the environment. And so that kind of thing should take us back to, the various kinds of figures that we've seen uh, over the course of the textbook, and this general sense of action perception cycles. Please. Well, in any case, we've seen this many times. This idea that, that the agent and environment are separated, right? Here we go. Um, we have the agent, we have the environment. There's no direct connection between the two of them. That's what this whole partially observable sort of framework or setting that we're in is really about. That's where a lot of notions of like subjectivity, the idea of Bayesian mechanics being a kind of subjective mechanics or mechanics of subjectivity. It's that we can't know the true hidden states of the environment, these true external states. So the best we can do is infer them. And so what separates us from the environment, but allows us to have some kind of vicarious relationship with it, make some kind of inferences about it, is our capacity to emit actions and our capacity to receive sensory observations. So to bring that back, whenever one is, setting up these different kinds of models, you have to create an environment that has that. And it needs to be able to emit observations and it needs to be able to receive actions. Or if you're only working on perception, then it doesn't need to receive actions, right? It's so in perception, it's just a matter of the agent is sort of passive and just perceiving what's going on without doing anything about it. Um, and it's the ability to kind of put together these priors in your D and your likelihoods that relates the hidden states to observations in your A, and then the way that hidden states change over time, the kind of discrete analog to continuous flow in the continuous case, being able to compose this of how one hidden state transitions to the next. So the probability of rainy transitioning to rainy, staying rainy, is what is that? Roughly a 0.7, 0.75, and so having those kinds of distributions set up. And then you can run this kind of Markovian chain-like logic where you are just employing Bayes' theorem over and over and over. And it's, from there that we already start imagining, well, what if this kind of inference is not tractable? What happens whenever our state space is huge and all the rest? And it's in that case that we do need to think about variational inference, and that's where suddenly the free energy principle comes once again back into the picture. Um, so given that we're quite low on time, I just wanted to briefly see, I know that there were some questions in the chat. Yeah, in the D and the observation. It's A. Right. Okay. So yeah, I would say in the kind of example with this hidden Markov model here, that we've discussed. So we have our priors over hidden states. So just so we remember how this was in the continuous case, our D here, prior over hidden states, and we have this one just denoting this is initial hidden states, saying at the very first time step, like before anything's really happened, this is our prior that we kind of come to the situation with. We're initializing our simulation, right? It's here that our priors will just be a single vector in this example, in this simple univariate example. It'll just be a single. All right, this doesn't like to scroll sometimes. It'll be this singular vector at the bottom here. Right, so we have this distribution over these different mutually exclusive hidden states. That's our prior. That is all that the D is. And whenever we run inference, it's there that we will employ it one time, only when we're at the first time step. Here, Namjoshi's use zero to use zero indexing. So this is the zeroth time step, but we're going to call it the first or very initial time step, right? That's where the agent will use its likelihood, just going to relate hidden states to observations, right? Because if you come to a situation where there's states and observations, but you only have a prior on states, then we've said nothing about observations. The agent has no encoding, no understanding, no sense of probabilities and relationships between how hidden states relate to these observations it's suddenly getting. That's where the A comes in. The likelihood, that's what allows us to make these statements about what is the probability of observations given hidden states or of any particular observation given a distribution of hidden states or given a particular hidden state. We can run those sorts of computations. So without the A, there's simply no relationship in our model for O and S, right? And if we have a prior on D, that's what gives us that starting point for Bayes' theorem on what the states are. So that whenever we get to, this general uh, way of looking at Bayes' theorem, where we know that our posterior is always a likelihood times a prior divided by evidence. And we know that this evidence term can just be a particular observation we get at a certain time. That's why in the continuous case, we're doing this clamping thing, right? Y equals a particular observation. Then all you need from there is you need a likelihood and a prior. And that's exactly what these A and D uh, distributions, categorical distributions, are all about. It's B that then gives a sense of flow to the state. It says, oh, but also the hidden state itself could change over time, right? And A and D alone would be enough in a static environment. You could just say like, yep, there are states, there are observations. What hidden state is it? Great, it's rainy. But what happens whenever the weather changes, right? This is nothing about the idea that states could change, right? It's just making probabilistic statements, but there's nothing in here that has any logic of B being, of hidden states being something that can change. So it's here by adding a B that the agent now has a sense of time and change over time. It has some sense that actually hidden states of their own accord can have some kind of transformation over time. In fact, the weather does change over time, right? Um, then let me just make sure I can. So at that time, but what about you? That can also go you. Yes. First, there is no necessity for D to be uniform. That is simply a recommendation for particular circumstances. That is it, someone who's doing computational psychiatry who has some theory that, an individual who's prone to exacerbated stress due to a stress disorder, they might have a higher belief about something about the environment. They might be biased in their view of how the environment works, or they're perceiving another person, trying to make inferences about another person. They might be inclined to believe certain things about that other person in a very biased way. If we wanted to represent that as a kind of probability distribution, we could very well not have a uniform D. We could say, oh, whenever our agent confronts that other person and they have this bias, and then one of these hidden states will be much more probable. Maybe our agent is not very trusting of others, right? So they see another person, and there are two different hidden states for that person, right? Either this person in front of me is trustworthy or they're not trustworthy. A uniform distribution would look like a flip of a coin, right? It would say, oh, trustworthy 0.5, untrustworthy 0.5. I'm not sure. I need to do some inference, right? I need to observe things about this person and potentially act as well to either try and elicit even more observations or find other ways to interact with this person. Um, right? It's there that updating can then begin, but the D is simply that very starting step of what do I think about you, given that I haven't observed anything about you yet, right? There's no O or Y variable in this. It's just the S. It's just the hidden states, right? Um, so it does not have to be uniform. I was saying that you can make it uniform if you're unsure of what it should be. You yourself is the experimenter, right? If you're trying to fit the model, if you're trying to, you have some real empirical data, you're trying to run some kind of inference over it to try and do something, then yeah, you can absolutely make it uniform, which will make it essentially not biased at all. All of its beliefs will be kind of equivalent to one another. It's like, well, you could be trustworthy, you could not be. That will allow me to approach this in a less, sort of predisposed, biased way. Um, and then similarly, you could do that. with the A matrix, right? If you did that, that means your model has the architecture to relate observations and states, right? You have an A parameter here, a whole tensor, a whole set of these, distributions that relate each observation to each hidden state or set of hidden states. So great. But if it's fully uniform, right, then that means it's not going to be able to distinguish anything. It's going to observe hot and say, oh, hot. Well, I have a uniform distribution over states for that. So it could be rainy or cloudy or sunny or snowy, each of them with a probability of 0.25, right? Like that would be a uniform A matrix. It would mean that anytime you get an observation, you're really not going to excuse me, you're not really going to update your beliefs much at all because you have no idea what this observation has to do with hidden states. And that's where all these questions about mappings, like many to many mappings, one to many mappings, many to one mappings. These are all, modeling problems that have existed for, decades. And they're the kind of thing that allow us to make claims about precision that we were seeing before. We recall in the continuous case, we were seeing precisions where, you might have a model that looks sharper. You might have a distribution that looks sharper versus kind of more spread out. And that relates to variance, where the higher the variance, the more it's kind of spread out around the mean rather than very sharp and precise around the mean, or in this case, mode. Um, but um, so that's the variance. Then whenever you take the reciprocal of the variance, that's where you have your precision, right? So very high precision would say we have a very precise kind of distribution here, whenever it's much sharper like this. A kind of analog to that is whenever you have a distribution that is not uniform, excuse me, that is not uniform. You can think of these uniform categorical distributions as having very high variance, right? Like it could be water, it could be hot, it could be bright, it could be any of those three things. It's not very concentrated around one of them, right? Whereas in this rainy matrix here, or tensor here, water is much higher, right? The only reason why this doesn't look like the way that we've been representing these normal distributions is these sort of, bell curves or humps, or as, however you like, is that there is no ordinality between water and hot and bright. This isn't a continuous scale. These are just three different things, and it's very convenient to plot them as bars, right? We can plot them as um, um, bar charts. They're also other interesting ways of using like shading. Here, there's a very faint shading in this, which was this is effectively an agent's beliefs about hidden states, where the black refers to probability of one, and then it was here at this third time step that the wrong note was heard versus what it sort of should have been according to the agent's beliefs. And so using this shading to represent, oh, there is more uncertainty here. This black is not a perfect 1.0 black. It's a little bit lighter than that. It's rough, perhaps it's like a 0.7 or something. And this slightly darker here is that this is the note it heard versus what it should have been, all the rest. So I hope that was useful in some kind of way. And it is very much the case that D and A can be hypothesis driven. I mean, they can be hypothesis driven depending on your scenario that you're setting up, right? I think in almost all cases it's going to be hypothesis driven unless you don't have one. If you don't have one, then going with a uniform distribution, that will kind of be sufficient. But it's really going to come down to the situation at hand, right? Um, so we'll talk more about that in the coming weeks. And again, I do strongly recommend having a look at PyMDP, having a look at SPM. I know that SPM can be quite a bit to get into whenever we have. The thing is that these scripts are really well developed, right? They have so much functionality that being able to get a sense of how they work, and not only that, but like starting with some of the easier examples. I mean, again, Ryan Smith. who's going to be speaking at the CPC in a couple weeks. He has a nice tutorial on active inference, and I mean, it's probably been the end all be all quick guide to getting into active inference in discrete state spaces, all the way down to making direct references to MATLAB and sort of, I believe it provides some snippets of code in the appendix, and then it makes references, yep, to, that SPM MDP VBX. It's incredibly long, kind of legacy style file names. But so I would strongly suggest that, it's really what do you want to get out of this textbook? Um, yeah, thanks, Ahmad, for sharing that. For sure, he has, I mean, he's given
It's a gift.
Oop, advertisements. Fun. Let's see. Oh, Berlin. Yeah, so this was several years ago. He's given many of these talks, and they're really great. I mean, one thing that we are not getting in this fundamentals textbooks that we're not getting very much relationship to sort of the neuroscience stuff. I mean, we are in the sense that we're getting all these philosophical and conceptual notions of what perception and action are. All of it is absolutely coherent with the active inference framework in general. But we're not going to see very much about local field potentials, right? We're not going to see very much about um, neurotransmission or modulation, other than a couple references to it whenever we were talking about attention in chapter 8, right? So, I mean, there's so much more kind of to learn in this field. I think that Sanjeev's textbook really is just something that will clarify a lot of the mathematics. And it clarifies the mathematics and it gives you a much broader fundamentals toolkit for thinking about how to make these models. And that said, it is a whole world whenever you look at continuous models versus discrete models. So it's great to draw out all these analogs between the two since we spent all this time on continuous. Uh, but in any case, I've certainly gone over on time, but I appreciate everyone's attention. And I think that maybe next week and especially the week after that, I'll allow more time for sort of discussion and question asking and answering, so that, if there are any continued, uncertainties or points of interest that people have or otherwise, we can actually talk through them. I just really wanted to be sure that we get through some of these fundamental aspects. And so again, the reference to the slides are all on the first page. Thank you, folks, so much. And yeah, we will see you hopefully this Friday with Fraser's session, and then I will be back same time next Tuesday. So yes, once again, thank you all so much. I will now stop the recording, but we'll also stop the session. So we'll see you soon. And per usual, please ask questions in the discourse and questions page on the superhuman coda for the textbook group. Thanks so much. See you at the next one.